Okay, hello everyone. So this will be the first video, and I'm just going to be going over some direct proofs that we are going to go. So this is just a simple question to get you acquainted with some direct proofs and indirect proofs. So we're going to start off with A, right? So A is if they are let A and B be integers, prove the following. So if A and B are both even, then their sum is also even. Now this is a direct proof, right? So it's P to Q, right? Q being Q over here being A and B are both even, then Q being their sum is even. So we want to prove Q using P. So we know that any even number can be expressed as 2n, n being any number, right? So for instance 2 1, that's even, 2 2, that's also even, and so on and so forth. So that's a general form of any even number. So in short, what they're telling us here is to say that A can be expressed in the form 2r and B can be expressed in the form 2s, where s and r are members of the integer class, right? So where s and r are some integer. Okay, so how are we going to prove this? Well, for our proof, all we're going to say is we know that A plus B. So we want to prove that A plus B is also even, right? But we know that A and B can be expressed as 2r plus 2s, right? In doing so, we can factor out the 2 over there. So we're going to say 2, then r plus s, which r plus s will also give us some integer. So you can say 2t. So you know that A plus B is equal to 2 by some number t, where t is a member of integers, right? And this is our first proof. So that's the most trivial proof that we can do. So just to go over it, we know that any even number can be expressed in the form 2n, where n is a member of the integers. Then for our proof, we just use these known facts and then we just express it in this form. We factor out the 2 there, and yeah, so we have our integer. So this is how you go about a very basic direct proof to prove whether the sum of two even numbers is also even. Okay, now on to the second one. So I'm just gonna rub this off. So for our second proof is B there. So if they are both even, then their product is also even. So again, we're going to say, okay, if A can be expressed in the form 2r and B in the form 2s, then AB is also even, right? So proof. How are you going to prove that? So we're going to say AB is equal to 2r, right, by 2s. If we multiply these two together, what we have is 4rs, right? 4rs is the same as saying 2 open brackets 2rs. We know that this is going to be some integer, right? 2rs is some integer, if assuming r and s are also integers as well. So we're basically going to have 2u, where u is a member of our set of integers. So just like this, we've proven that, okay, if we have A and B, multiplying them, if we have A and B, multiplying them, and if they are both even, then their result is also even. So this is a very simple direct proof, again using the concepts from the previous question. Now go on to something else. So we're going to just finish this question in this video, then yeah, we'll have another one. So if their sum is even, then both are even, or they are both odd. Now this one over here is a proof by case. So a case is where you go over all the possible cases and then you prove them. So if their sum is even, so if their sum over here is even, then they are both even or they are both odd. So over here we have two cases, one where both integers are even and one where both integers are false, are odd. So for our first case, so you say, let me just, okay, so we have Okay, so we have our proof there, so always indicate that you're proving there. So we have our proof, then we're going to say case number one, right? Our case number one is where they are both even, right? Again, this is similar to this is a similar proof to what we've been doing all this time. So this is similar to A. So I'm just going to say A is equal to 2R, B is equal to 2S. Then we're just going to say A plus B is equal to 2R plus 2S, which gives us 2R plus S, which is equal to 2T. So then just close it off with a QED there, right? So this is our first proof. This is something we've been doing all along. But then, what of the other proof? The case where they are both odd, right? So in the case where they are both odd, so case number two. So always remember to label all your cases. So case one, case two. So case number two, both are odd, right? Now for an odd number k can be expressed in the form 2n plus 1, right? This is a standard form for an odd number, or it can be expressed another way, but for our purposes we're just going to express it like this. Of course you can always go in and express it okay, it's fine, but just for a simple proof of this one, I can put in a 1 there, plus 1, that gives me 3, 2, that there, plus 1, which gives me 5, and so on and so forth. So that's just the basic form that we're going to be using for now. So in this case we're going to say A is equal to 2S plus 1. You can use any other letters, I'm just using S and R because they're the only things that come to mind. And then B is equal to 2R plus 1, like that, right? So we're going to have these two, and then we're going to add them together. So A plus B, right? A plus B is equal to 2S plus 1, right, plus 2R plus 1, which gives me 4S. No, those two can't be added together. So we're going to have 2S plus 2R, 2S plus 2R plus 2 there, right? All of these have 2, so I can factor out the 2 there. So I'm going to say 2S plus R plus 1, which of course gives me 2 by some integer V, right? Where V is a member of our integer set, right? In doing that, we can say that, okay, since 2V, right, 2V, this is an integer here. So we've proven to say if they are both even or they are both odd, our result is still an even number because it's still in the form 2 by some integer. So this is how you go about this proof, right? So yeah, this was supposed to be C. Yeah. So this is how you go about this proof, and it's a direct proof by cases. So yeah. So for the next proof, I'm gonna say D, right? For the next proof, this one, if their sum is even, then so is their difference, right? So if their sum is even, then so is their difference. Now this one is a bit more complicated than this. It's not extremely hard, but it is a bit more complicated than this. So what we know here for our proof, so the knowns here, what we know here is that A plus B, so our knowns, A plus B is equal to 2m, right? A plus B is equal to 2m, right? Then what we want to prove is A minus B. So how are we going to do that? Well, the first thing is we're going to use what we already have in order to we're going to use what we already have, in short. So we're gonna say A plus B. We know A plus B is equal to 2m. Then we're going to make any one of these subject of the formula. In this case, let me just make A subject of the formula, and then I'm going to have A is equal to 2m minus B, right? Then now we want to prove And so I'm just going to draw a horizontal line here. Then I'm going to say a minus b, right? Now this guy can then be expressed. So we have our value of a from the stuff that we already know here, right? So I'm going to say 2m minus b minus b. So this guy here is coming from this one over here. So in doing so, we have 2m minus 2b, right? Which, when you factor out the 2 there, we have m minus b, which is equal to which is just equal to 2 by some integer t, right? Where t is a member of our set of integers. And that's how you do that direct proof. So even say QED there. Yeah. So this is the end of our proof. So just to recap, first of all, we know that a plus b is even. So what do? First of all, we choose any one of these to make subject to the formula, because we can't directly prove this without certain information from here. So we choose any one of these to make subject to the formula. In this case, I chose a. So we have a plus b is equal to 2m, which after making a subject to the formula, we have a is equal to 2m minus b. Then we go to what we actually want to prove, where their difference is also even. So we're going to say a minus b is equal to 2m minus b over there. Then we're going to have, okay, then yeah, we just solve it normally. So we add these, we collect the like terms, factor out the 2 there. What we have here, since both of these numbers we know they are integers, mean that even their difference will also be an integer, and then we have that there. So this is how you go about this simple proof. Yeah. So yeah, this would be all for this question specifically. In the next video we'll also have another set of questions. Yeah, bye.